Professor. Why are you
Hey.
dressed like a magician?
What's up there, Junior? Hi, Jennifer. Well, I'm dressed up like a magician because today I'm going to do a magic trick. I'm going to take this little beaker and I'm going to break it into small little bits, make it disappear, and then make it reappear whole again.
Yeah, sure, Professor.
I'll believe it when I see it.
Well, you just watch. All right, so what we're going to do is we're going to take this bag, we're going to put this beaker in it, put it in there nice, set it up here, cover it with a scarf. Remember to get your folks or an adult to help you with this. We're going to cover it up. I think I got a hammer here somewhere. We take the hammer, stand back a little bit, and we're going to whack it a good one, okay? Okay, so now we've got that glass broken up real good in there. Hear it? Broken up pretty good, right? Okay, now we're going to add that into this beaker carefully. Again, have mom and dad or an older brother or sister help you with this. There's the contents. That's the smashed up beaker. We're going to add a little bit of oil here. Oh, I'd say about 1,000 milliliters. What do you think, Junior? All right. All right, here we go. Boom, that's about enough. All right. Now, are you ready? And then I'm going to take my magic scarf, put it over it like this. A few incantations. Abracadabra, splinky pop top. And then, voila! There you have a whole beaker.
Hey, how did you do that?
Well, it's a magic trick using the trick of light. And that's what today's show is all about. Light. What is light?
Well, light helps you see.
Yeah, it helps you see. Junior?
It's a source of power.
Yes, that's right, it is. Determining the true nature of light has perplexed scientists for hundreds of years. Now, Newton hypothesized that light oftentimes behaved like particles, but his contemporaries thought light was made up of waves. Now, the disagreement amongst scientists as to whether light was a particle or a wave continued for nearly 300 years, and it wasn't until Albert Einstein explained that a particle of light, or photon, could actually hit an electron and knock it out of its orbit around an atom in a metal that Newton's hypothesis was proven right. Einstein was actually awarded the Nobel Prize for his explanation of the photoelectric effect, which proved the Newtonian hypothesis, and not for his special and general theories of relativity. Today we'll do a few activities that helps explain the way light behaves. Light is a form of energy, and it's the fastest moving energy we know. Light travels at the speed of 300,000 kilometers per second, or 186,000 miles per second in a vacuum. A vacuum is a place without air. Unlike sound, which cannot travel in a vacuum, light can travel through air or a vacuum, or other materials such as glass or water. Now, we'll talk about this later. Remember, light travels at different speeds through different materials. We can easily observe that light travels faster than sound during a thunderstorm. Think about it. What do you observe first? The sound of the thunder or the flash of the lightning?
The flash of the lightning.
Right. We see the lightning before the thunder can be heard because light travels nearly 1,000,000 times faster than sound. We see the light nearly instantly, and the thunder can take several more seconds to reach our ear. It's only if the lightning strike is very near to us that the sound and light seem to occur simultaneously. Light travels through space in a straight line, but when it meets another object, it can change direction. Like a mirror can reflect the light, much the way a ball might bounce off of a hard surface. Traveling through different material will slow the light down. Materials like water will refract light. When the light goes from air to water, its path will slightly change direction and form what we know as an optical illusion. Now, before we discuss reflection and refraction, let's talk about the material that light can pass through or bounce off. All right, now we're going to do an activity it'll show us how light passes through things. Now, Junior, you hold this piece of cardboard and hold it up in front of you. Hold it right up in front of you. Now, can you see me?
No.
No, you cannot. Now, Jennifer, you take this wax paper, okay, and hold it up right in front of your eyes, right, like that. Can you see me?
Yes.
How do I look?
You're a little blurry and fuzzy.
A little blurry and fuzzy. Now, I'm looking at both of you guys through this clear plastic, and I can see you almost perfectly, at least good enough to drive a car. Now, the reason you couldn't see me through this, Junior, is because it's opaque. Light will not pass through it. And Jennifer, the reason why I look fuzzy is because wax paper is translucent, okay? That means it's diaphanous. Some light will pass through it, but not all light. And the reason I can see through this real well is because it's transparent. Opaque, transparent, translucent, okay? Okay, now let's do a simple activity to explore the concept of refraction. Now, you've all seen this idea if you've ever observed the way a straw looks in a glass of water. Junior, fill this beaker with that flask right there. Fill it up about half full, please. Now, Jennifer, I want you to take this pencil and immerse it in the water, but make sure you go straight up and down and just a little bit off center towards the edge of the beaker. Hey, you've broken it.
No, I haven't. It's still one pencil.
All right, well, what do you suppose happened?
The water bent the light rays?
Right. Junior?
It seems the water acted like a lens.
This has to do with refraction. The fact that the light rays from the pencil travel from a denser medium, the water, to a less dense medium, the air. Light rays bend when they leave the surface at an angle other than straight out. The pencil is seen at the extension of the bent ray, and it looks as if the pencil broke and part of it moved away from the other part. The pencil is also magnified. This bending of the light rays is called refraction. Now, what happens if you place the pencil in the center of the beaker? Jennifer, you try it. Stick your pencil straight in the middle, straight up and down, and what happens?
It doesn't look broken, but it's still magnified.
Now, reflection is something we all take for granted, right? When do we see reflection?
When we look in the mirror?
Right. And we use mirrors to see how we look. We also use them in our cars to help us see along the sides or the rear of the car behind us. Now, there are many things we use mirrors for. They are even a part of instruments like cameras and telescopes. But how do they work? A mirror, as we said, reflects light and bounces it back to our eyes. But what we see in a mirror image is not the real image, as the mirror itself does not generate any light. There is no light coming from behind the mirror where the image appears to be. Now, if we hold up a picture to a mirror, what happens?
It looks backwards.
So, when you look at yourself in a mirror, you're not seeing the you like everyone else sees you, are you?
No.
No, you're not. Well, let's trick the mirrors and get a look at what we really, really look like. Okay, now, Jennifer, what I want you to do is take these two mirror tiles here and hold them perpendicular to one another. That means at a 90-degree angle. Now, Junior and Jennifer, I want you to take turns looking at your reflections. But don't look in one mirror or another. Look directly into the corner where they meet at the 90-degree angle. Okay? Now, Jennifer, put your right hand on the back of your head and tell me what you see.
My hand's on the opposite side of my head.
Exactly. Now, Jennifer, using just one mirror, look straight at it and do the same thing. What's happening? It's on the same side, right? Yeah, it is. Well, which is the real you? When the mirrors are perpendicular, you see you as others see you. For instance, if I put my right hand on my head and you put your right hand on yours, go ahead and do it, Junior, and we face each other, our hands look opposite, right? But they're not, are they? No, no. Now, think about the photo we put in front of the flat mirror. It was reversed, right?
Right.
Right. So, are you in a flat mirror?
No.
No, you're not. Now, let's take this picture right here and put it right in the corner, right in the 90-degree angle. Now, both of you look at that picture and tell me what you see.
It looks exactly as it's supposed to.
Right. So, what happened in the cornered mirrors? The light rays of the object are reflected in 90-degree angles from one mirror to the other and then back to the eye. In a regular flat mirror, they bounce right back to the eye without being reflected twice. With the two mirrors perpendicular to each other, anything on the left of the object is reflected to the right-hand side. Now, all the points on the object on the left side is seen on the right side and vice versa. And this is exactly how others see you. Now let's talk a little further about how we see things. Now, some things generate their own light, like the sun or a light bulb. The reason we can see things that don't give off their own light is because of the way the light rays bounce off of them and are reflected. The moon is a perfect example of this. It doesn't generate any of its own light, does it? And yet you can see it clearly in the dark night sky because it's reflecting light from the sun. An object's texture and color will help determine how well it can be seen. A smooth white object reflects all color of light the best. An object that does not reflect light at all looks black. But what color is light, Jennifer?
Yellow.
Yellow? That's what I think of when I draw a light. I draw it yellow. What do you think?
All the colors.
All the colors of the spectrum?
Yeah.
Yeah. Roy G. Biv, you ever hear of that?
Yeah.
That's the colors of the spectrum. We'll talk about that a little bit later. Now let's find out about that. Light travels in waves. If we take this rope and shake it up and down, we can see the way light waves would look if we could actually see the waves. Of course, it'd be much faster than this. You see that? Waves just like that. That's exactly how light waves travel. Now, if you've ever seen a rainbow, then you already know all the colors that exist in light. The water particles in the sky from the rain, combined with the sunlight, refract to show each individual wavelength of the colors that make up light, just like you were saying before about the spectral colors. Now, what are the colors in the rainbow? Do you know?
Red, orange, yellow, green, blue,
Indigo.
indigo, and violet.
Exactly. Very good. Most people say what?
Roy G. Biv.
Roy G. Biv, exactly. And that's a perfect way to remember the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and violet, right? Roy G. Biv. Now, this is a prism. And if we shine a beam of light through it, we'll see all these colors. Now, one of our technicians set up a very high-power light over here so that we can look through this prism. See, here we have the colors. We have red, orange, yellow, green, blue, indigo, and violet. When light is broken into all of its colors, as in a prism, this rainbow array is also called a spectrum. Now, all colors together look white, but sometimes two or more waves of the same frequency can combine to alternatively cancel each other or add together. Now, this is called interference. Now, here's another activity that we can use to show interference. Junior, I want you to take this bowl of water. I want you to take a drop of this clear nail polish and see if you can just drop one drop right on the surface of the water. Go ahead. There you go. You see that? Now tell me what you see, Junior.
I see colors.
I see little rainbows.
Right. The nail polish forms a thin film across the water. When light rays strike the film, part of each ray is reflected from the surface. Part of the ray goes through and is reflected off the bottom of the film. Now this is the same as the oil on the surface of a puddle. Do you ever see that on a rainy day?
Yeah.
See that? Now, if the reflected rays overlap as they leave the film, they'll interfere with each other, causing colors that we see. Now, the timing has to be just right for the reflected rays from the surface and the bottom of the film to meet as they leave the film. If this doesn't happen, there is no interference, and then areas without colors are seen.
Professor, your magic trick with the beaker, how'd you make it disappear?
Ah, yes. Well, that little trick has to do with refraction, and here's how it works. We found out today that we see opaque objects by the way they reflect light. Transparent objects, on the other hand, light just passes right through. So why can we see objects such as glass or plastic at all? Well, the reason we can see it is because it has bent angles. And there's everywhere light hits it, you can see reflection down here, you can see shape, you can see shadows, you can see droplets and everything else, because it has shape to it, it has form. Now, when light passes from one material to another, let's say from air to a glass door, its speed changes, so the light bends. The bending of the light also distorts and changes the appearance of objects behind a transparent one.
Like the pencil in the beaker?
Yes, exactly, like the pencil in the beaker. So, we can tell the glass is there by the distortion of the objects behind it. Now, here's how I did my magic trick. Before you showed up, I had already hidden a small beaker in the larger one and filled it with oil. I showed you another small beaker, and then I broke it. And then I dropped the broken pieces into the larger beaker, where they too seemed to disappear. Then, voila! I pulled out the hidden small beaker, which you couldn't see. Now, the beakers and the oil have something in common. Light travels at the same speed through both of them. That means that once light enters the oil, it travels straight through the beaker without bending, and that makes the broken glass invisible. A light trick fooled your eyes. And that's the magic of light. And there's a lot of light tricks you can play at home. But make sure you always get a grown-up to help you out, especially when you're using glass, okay? And remember, science is fundamental.